Hello, ladies and gentlemen, and welcome back. Root Beer here, and we are looking at our very last question 25, on the 2016 Fermat paper. Okay. The set A of 1, 2, 3, everything up to 2045, which is not a perfect square. For a second there, I'm thinking 2025. Which is 45 squared, and that might be why my brain is getting confused. But this set contains 2045 elements. I agree with that. A subset S of A is called triple free if no element of S equals 3 times another element of S. So if S is in the set, 3S is not in the set. And if 3S is in the set, then S is not in the set. So there's sort of a mutual exclusivity going on there. Alright, so that's what it means to be triple free. For example, 1, 2, 4, 5, 10, 2043 is triple free. But 1, 2, 4, 5, 10, 681, 2043 is not triple free. Because if I triple this, I get this. Okay. But if I removed it, we'd get this set again, and that would be triple free. Or I believe I could remove the 2043, and it would also still be triple free. Alright, the triple free subsets of A that contain the largest number of elements contain exactly 1,535 elements. Interesting. Okay, there are n triple-free subsets of A that contain 1,500. So n of these sort of maximal, largest possible triple-free subsets. So there's n of those. The integer n can be written in the form. Wow, this is a long setup here. This can be written in the form p to the a, q to the b, where p and q are distinct primes, a and b are positive integers. If capital N is p squared plus q squared plus a squared plus b squared, then the last 3 digits of n are. Okay, so there's sort of a lot of setup just to get the answer that they want to give well after you've figured out what this little n is. And that's because I believe around this time they were trying to experiment with ways to stop people from guessing on the last question just to get 8 marks. I mean, you can get 2 marks for leaving the question blank, but some people don't do the probability in their head and they will still guess anyway. And I think they were getting a lot of people who would get 150 on the contest but have no idea how to actually do 25 or 24 just because they happen to guess. And if you got thousands of students writing it and they start guessing on the last couple, well, some of them are bound to get perfect on the paper without knowing how to do the harder questions. So there's sort of no way to narrow it down with all these answers here. You know, is it 402? No idea. But there's, you'd have to figure out the exact value of n and then go through all this setup just to get, your answer. Okay. Well, we have to figure out what the little n is, and then we go through all this setup. And we'll know we're on the right track if it can be prime factored as, 2 to the something, 3 to the something, or, 2 to the something, 5 to the something, or 3 to the something. If it's got only 2 prime factors, we'll know we're on the right track. We also might guess, we might be able to determine the sizes of the sets we're making and double check that, yeah, these are all have 1,535 elements. But the 2,045, that seems pretty big. So, I think I'd like to take a look at a smaller sort of situation. Now, I want it to be big enough that some interesting things might happen. So I'm not just going to look at, say, 1, 2, 3. Although we could, we could call that our A and see where we can go from there. But I don't think there's going to be too much that's interesting. I think what I'd like to do is start taking a look at least up to 9. Now, why am I choosing 9? Well, they're talking about triple free. And so, for example, if I let 1 be in my set, 3 definitely can't be in my set. Right? But if 3's not in the set, then we could include 9. So this is sort of a a geometric sequence of size of common ratio 3. And if you're not familiar with what a geometric sequence is, you start with a single term, and then each term afterwards you multiply by this common ratio r to get the next term and the next term and so on. So what we've got is a geometric sequence where the common ratio r is 3. So I think that might be interesting. Now, if we're going to look at this set, and this also might be too small a set to actually do anything, but I think the 9 will add some spice to what we're about to do. But let's see if we can answer the question from here. If it was not 2045, let's look at this smaller case that's easier to manage. Maybe we can list everything out, and hopefully we can recognize some patterns. So, in terms of patterns, well, what numbers could we have? So, for example, I noticed 4. 4 is not a multiple of 3, and 12 is not possible. So 4 we can automatically add. And remember, we want to add in as many things because we're concerned with counting these, what we might call maximal subsets, contain the largest number of elements. So 4 should definitely be added in. Same with 5. Now 6 we would pair up with 2, because that sort of forms a geometric sequence of length 2. And I guess 4 by itself is a sequence of length 1. But 7 and 8, you can definitely add those. 1, 3, and 9, however, those guys are interesting. So we should definitely have 4, 5, 7, and 8. And then, well, we have a choice. Do I add in 2 or do I add in 6? Adding 2 over 6 doesn't increase the number of possible numbers. It's almost like we just need to look at things in terms of just sort of unions of geometric sequences of length 1. But, adding in 6 doesn't affect whether or not 1 should be added in. They're not multiples of 3 away from each other. So I have two choices, add in a 2 or a 6. And then when it comes to 1, 3, or 9, I guess we could add in a 1. And then we could also add in a 9. But I'd have to avoid adding in the 3. Or I guess we could add in the 3, but then you can't have 1 or 9. So 4, 5, 7, and 8, they have to be added. So if I'm making a new, what do we call it, triple free set, definitely going to have 4, 5, 7, and 8. I'm going to have 1 of 2 or 6. So I could have 2 here. Or we could have 6 so that we could make another one. 2, 4, 5, 6, 7, 8. But when it comes to choosing something from my set 1, 3, 9, that geometric sequence, well, we can't choose. It looks like it could be 1 or 9 or add in 3, but we want the most elements possible. If I add in a 3, I could find a bigger set that has the 1 and the 9, so this would not be a maximal set. So we'll add in the 1, 9, and that should be it. And this contains all but 2 elements. So these are of size 7, and they contain only 2 elements. And, sorry, not only 2 elements. There's only 2 possibilities, and that comes from the choice we make here with 2 and 6. So, I want to focus on these geometric sequences. So, suppose A is just some number of natural numbers. I don't think the 2045 actually matters here. So, we'll just look at the first K numbers. What we really want to view this as is sort of... Actually, no. I want to explain this rather than answer the question. So if I look at it 1, 2, 3, 4 up to 9, what we're really doing is looking at this as 1, 3, 9. That's a geometric sequence. 2, 6. That's a geometric sequence. 4 is a geometric sequence where and all of these are being made with a common ratio of 3. So you could probably do this question with quadruple free sets or things like that. Okay. But if I break my set down into the various geometric sequences where the common ratio, the thing you multiply, is 3, what we're really doing is we're trying to just choose the most numbers from each of these. And so the most numbers I can pick from these are, well, those numbers. I have 2 choices here. Do I pick a 2 or a 6? And then, well, for this one, I've got to pick the 2 end ones. So what if I did something like 27? Because that's another power of 3. So all the way up to 27. So what I'm going to do is I'm going to write this in terms of its geometric sequences. So 1, 3, 9, 27. That's the only one of length 4, with 4 terms multiplying by 3 each time. 2, 6, 18. And you can't go further than that and still be in this set. Don't need anything with 3. 4. Can we do 4? 4, 12... multiplied by 3, that would be 36, so no. I mean, we can still do 4, but I'm going to put it down here. So 4 and 12. 5 and 15. 6 and 18 are already covered. How about 7, 21. 8 and 24. And then 9's already covered. So, and then we'd get 10. 10 times 3 would be 30, so that's not included. It's just 10 by itself. 11. 12 is done. 13. 14. Basically all the ones that aren't multiples of 3 at this point. So not 15. 16 certainly. 17 is technically it's a geometric sequence of length 1 all by itself. 19, 20, 22. We're skipping 21 because it's already included up here. Skip 24, but we will do 25. And 26. So there's everything, but it's broken down into, here are the geometric sequences of length 4. These ones are the ones of length 3. This group is length 2. And these ones down here are all the geometric sequences that are really just sequences of length 1. But now when it comes to making this set S, I get to include each one of these because there's no competition. Include 14 because there's no 42 available. So automatically get to add everything from there. We get 2 choices. Do I add in 4 or do I add in 12? Adding in 4 only eliminates 12 from the possibilities. Has no effect on whether or not the 6 gets added or the 27 or anything like that. These you can sort of think of these geometric sequences as sort of their own little ecosystems. But do I pick the 4 or the 12? 2 possibilities. 2 choices. Do I pick the 5 or the 15? 2 choices there. The 7 or the 21? 2 choices, 2 choices. So it looks like right now there could be 8 different S's that we could have. 4, 5, 21, and 8. Those could be in, along with all the ones down here. Just like before, now that I have a sequence of length 3, I have to include these 2 endpoints. If I just included the 6, that would mean the 2 and the 18 can't be included. And those ones, that would make it a smaller sequence, and we need S to be as big as possible. So you're forced to have the 2 and the 18. But do we have options? So I could have 1 and 9 included up here. So the 1 excludes the 3, and then we choose the 9 to exclude the 27. And that's good. I could have the 1, can't have the 3, maybe don't have the 9 and have the 27. That's another possibility. Or we might not have the 1 at all. We can have the 3, then I can't have the 1 or the 9, but I could still have the 27. So there's sort of 3 possibilities here. So if I put this all together, the sequences of length 1 all get added in. Any sequence of length 3, the two ends have to be added in. But looks like the even length sequences of 4 and of length 2 have options. 2 times 2 times 2. So it looks like there are 16. So 2 to the 4 times that 1, 3. Many maximal or largest containing the most elements. That's what maximal means. Okay. Now that looks good for a couple reasons. One, I like that I'm breaking it down in terms of the geometric sequences, because that's really all that triple free is about. Is if you are part of a geometric sequence with common ratio of 3, is there a term, and you're in this set S, then there's no immediate term after you or before you in your geometric sequence that's also in there. That's all it is. So 8 being in has nothing to do with 18 being in. Breaking it down like this allows me to realize that. But I'm also happy because look at our answer. It looks like a single prime to a power times a single prime to another power. Okay. So, are we ready to try and jump up a bit? So, I'm going to get 2. So let's see. If I say something like S, 3S, 9S. These are basically my sequences. So if I've got 3 to the KS is a maximal geometric sequence, by which I mean I'm not missing 3 to the k plus 1s or s over 3 or anything like that. Let's get rid of the term. I think maximal is too much. Let's say is a geometric sequence. In A, if k is even, then since this is technically 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, there are k plus 1 terms. And k plus 1 is odd. And what did we see? If you've got odds, like sequences of length 1 or of length 3, you are sort of forced to have we must include every other term starting with S. So we've seen this before, you know, if I did 1, 3, 9, 27, 243, what are some 729's the next one, 2187, that sort of a thing. So there's its odd length. You'd have to include 1, 9, 243, and 2187 because that's the most you could add from this group. So if we have an odd length geometric sequence, there's no choice, there's nothing we can do. But if it's even, so that is to say, if k is odd, k plus 1 is even, and we have choices. And figuring out where our choices are allows us, using sort of combinatorics or finite math methods, to figure out how many sets S there are without actually listing them all out. So when I had 2 sets, I could pick S, or sorry, 2 things in my sequence. I could pick S or I could pick 3S. Adding 1 just excludes the other one. And then when we had 4 things, so k being equal to 3, we had S9S could be added, S27s could be added, or 3S27s could be added. So that was 2 choices, 3 choices. What if I went a little further? What if I had 81? Oh, did I forget 81? I did forget 81. There we go. Now, technically, the notes are correct. 81S is the next one. And then 243S. Yeah, so that's 6 of them. So if I had 6 of them, let's use colors. I could have S, can't have 3S at that point. But we could do 9S and 81S. Or we could have S, 9S, you can't have 27S. Maybe we skip over 81S and jump straight to the 243S. That would still be of length 3. Notice you couldn't have any, you couldn't add 4 of these. Because you need to at least have gaps of every other one. So the most we can have is 3. We're just trying to figure out how many different sets of 3 we could take. So there's 2 of them. We could have S. We could have not have 9S, so 27S, and then go to 243S. And then I think that's it for S. I guess we could have 3S, and then have to have 27S, and then 243S. So that would be 4 choices. So I'm willing to bet, so this was K equals 3. This is K equals 1. Oh, sorry, this is K equals 3. This is K equals 5. So if K is equal to 2I plus 1, because K is odd, there are I plus too many choices. Of which I plus 1 elements to add. 2S. Okay. So, that would give me 2s, 3s, 4s. And 4s is just the power of 2s. But... Well, so with 2045, the next highest power of 3 is 2187. So the longest sequence I could have is 1, 3, 9, 27. And there'll be a couple of this length. But it will never go too far. So that's 1, 2, 3, 4, 5, 6. So I'll never have a sequence of length 8. So K will never be 7, because if K were 7, we'd get 5 choices. And then when we multiply everything together, you'd get a powers of 5 in my expression for the little n answer. Okay, so that's the longest sequence we can have. So, I know if everything is decomposed into various geometric sequences of their largest lengths, how to figure out the number of subsets S there are. So how do I figure out how many geometric sequences of a given length there are? So, what do we do? Well, with 9, there was one of length 3, and there was one sequence of length 2, and there were 4 sequences of length 1, which is not the most helpful thing out there. So I feel like we might have to bust out some logarithms here. Sort of what's the largest possible sequence, geometric sequence length for this? I feel like it's going to be log 3, I want to say floor function. So we know the longest sequence 1, 2, 3, 4, 5, 6, 7. So 7 is the longest you'll get in here, and you might get a few of those. And what is log of 245? Incidentally, if you're going to grab your calculator to do this sort of calculation, your calculator might not have log base 3. Mine certainly doesn't. But your calculator will likely have a log button. And what you can do is log and then divide by log 3. And that'll get you log base 3. And this is a nice rule about logarithms. I'm just reminding you of it in case you're not familiar with it. But I get 6.9 something. So if I were to floor that, it would be 6, which is 1 less than the 7. So do I need the ceiling? Do I need to use the ceiling function? Because then that would get me 7. Well, what would that do for 9? So that would get me log base 3 of 9, which would be the ceiling of 2, which is 2, but I know the longest sequence is of length 3. So I think we floor function and add 1. Because then that'll be 6 plus 1, which is 7. And this will be 2 plus 1, which is 3. Alright, so that's the longest sequence, but how many sequences of length 7 are there? That's the tricky thing. So, well, I suppose I get a fresh sheet of paper here. Okay. So how do I count the sequences, the length 7 geometric sequences? Well, basically I need to count. So 1, maybe I shouldn't count the base, maybe I should count where they end up. It would be the multiples of 729, right? Yeah, because a sequence of length 7 must look like this. A geometric sequence of length 7 has got to look... I keep forgetting 81. Why do I keep forgetting 81 today? So it'll look like this, and this number here, the 729S, has to be less than 2045. So how many of those are there? So divide it by 729. So S has to be less than about 2.805. So S is either 1 or 2. That's it. Okay. So there are 2 sequences of length 7. How does this help me from here? And does this work for my sequences of length 9? Yeah, 9S... Oh, sorry, this should be less than or equal, but... Alright. But a sequence of length 7, so there's two sequence of length 7. A sequence of length 7 doesn't contribute anything because you automatically alternate, and those numbers have to be added in. So, what I can say for certain is in any one of these triple free subsets S, 2 will have to be in there. So will 1. So will 6. They're guaranteed to be in there. Or sorry, not 6, because 6 would be here. 18. 18 would be something that's guaranteed to be in there. So there's two sequences of length 7, but what about the sequences of, say, a length 6? So a sequence of length 6 is going to look like S, 3S, 9S, 27S. This time we remember the 81S, 243S, and 243S again has to be less than or equal to 2045. So divide that by 243 on my calculator. S has to be less than or equal to 8.4. So S could be 1, 2, 3, 4, 5, 6, 7, or 8, except if S is 1 or 2, then it's already this situation here. So I guess what we need is 243S to be less than or equal to 2045, but 729S to be greater than, and that gives us two inequalities. So that should tell us how many sequences of a certain length. Oh, but you can't have 3 or 6. Because while those do give us length sequences that start at a certain number and end at this length, we can't have S be divisible by 3. Otherwise, you'd be able to sort of rewind time and have a smaller term in your sequence. So this equation, or these two inequalities, ensure that 243S is the largest term appearing in A, and this ensures that S is the smallest term in my geometric sequence, and that it can't be enlarged either way by adding an extra element of A. So that would be 4 there. Okay. Good to know. So there's 4 sequences of length 6, 4, and so on. In fact, I'll just double check on my calculator. 8 times 3, 24, times another 3, 72, times another 3, 216, times another 3, 648, times another 3, 1944, and times another 3 would be too big. Alright, now if I want a sequence of length 5. Also, for each of these 4 sequences of length 6, we would get 4 different choices for which elements to add in. So we have 4 to the 4 different possible S's so far. Alright, S, 3S, 9S, 27S, 81S. I don't think I care how many of these there are because they don't add anything to it. But what would we need? 81S would need to be less than 2045. 243S. Now, we will have worked this out from the previous one. So 8.4 has to be less than S from here. And this one here, 2045 divided by 81 will be, S has to be less than or equal to 25. Specifically 25.2, let's say. Because eventually 2045, oh no, 2045 is never a multiple of 3. Okay, we won't have to worry about that. So those are the S values, but we don't want to count multiples of 3. So how do we ensure that happens? So no 9, no 12, no 15. So which ones do we allow? 10, 11, 13, 14, 16, 17, no 18, no 21, no 24, 19, 20, 22, 23. So 2, 4, 6, 8, 10 of them. So there's 10 of these sequences of length 5, but they don't add anything to the story. They don't give me choices because I have to add in every other one. Okay. So, what can we say here? S would have to be specifically in this range, because I don't want to write all the ones out in future, because that's going to be too many. So how can I tell that S being between 9 and 25 tells me that there are 10 of them? So you want to subtract away the multiples of 3. 25 minus 9 is 16. Divide by 3 is 5. But I'm not removing 5 things. I removed 6 things. So 16 minus 6 is 10. Alright. Now, sequences that are just of length 4, these will actually contribute. Each one of them has 3 different ways to add in 2 elements to the set S that we are trying to create. And we need 27S to be less than or equal to 2045. And that needs to be less than 81S. Okay, so from here, from the previous one, we need 25.2 to be less than S. And should be 75.7. Alright, so strictly S is between 26 and 75. 75 minus 26 is 49. Divided by 3 is a little, it's just over 16. So I want to remove 16 elements. So I'd be removing 27, 30, all the way up to 75. So that's 3 times 9, and that's 3 times 25. 25 minus 9 plus 1 is 17. Why didn't I add 1 for the total number of numbers? That doesn't make sense to me. So between 25 and 9, 25 minus 9 plus 1, because we're being inclusive. Oh, I never added 25 down here. So yes, it should be 11. Okay, good. So there's 17 numbers inclusive here. And this should be plus 1. So there's actually 50 numbers inclusive. 50 minus 17, there should be 33. And each of these has, as we've seen, 1, 2, 1, 2, 1, 2, 3 different ways. So we're contributing 3 to the 33 to our numbers of number of ways we can make S. So 4 to the 4, 3 to the 33. All right, it's looking good, looking nice. All right, of length 3, so we'd need 9S to be less than or equal to 2045, and we need 27S to be greater than that. So S is at least 75.2. So S is definitely 76 or more. And 2045 divided by 9 is really the 75.2 multiplied by 3. But so less than or equal to 227.2. Okay, now 227 minus 76 plus 1 because we're being inclusive. This is 152 numbers. Divide by 3. 50 of them should be multiples of 3. So from 78 all the way up to 225. 78 is 26 times 3, and 225 is 75 times 3, which curiously are the previous numbers that I would have had. And so there are 50 numbers in here. So I subtract away 50. This is interesting. This 50 here, because we also subtracted away 17, which was the previous numbers I had, and we subtracted away 6, which was the previous numbers we had in this range other than the 1 and 2. And we subtracted from them 2. Interesting. Very, very interesting. But we're almost at the end. In fact, we're almost at the end of the question, so it doesn't really make sense to divert to double check or to develop some theory about this. Let's just get an answer. So that would be 102, but these don't do anything because you always include the first and last elements, so it doesn't really matter. Okay. The last thing we need to worry about would be S and 3S, because each of these, there's two options as to which numbers to put into the capital S set that we're making, the triple free set. So I need 3S to be less than or equal to 2045, and 9S to be greater. So what was it? 227.2 has to be less than S. Has to be less than or equal to whatever that is multiplied by 3. 681.6. So S is 228 through 681. Which is a total of 454 numbers. In theory, I should subtract off 152 of them. But let's double check that. So multiples of 3. Well, we start with a multiple of 3. And the last multiple of 3 is... Oh, 681 is also a multiple of 3. Okay. So 228 is 76 times 3, and it should be 227 times 3. And indeed it is. And so that should be 152. Exactly as predicted. So 454 minus 152, and that's going to be 302. And so each of these, there's one choice, do I include S, or another choice, do I include 3S, so 2 to the 302. And everything else will automatically get added in because it's not part of a geometric sequence, so it doesn't impact being triple free. So the number of different S's is 4 to the 4, 3 to the 33, and 2 to the 302. But we need to have it as a prime factorization, so we'll change this to 2 to the 8, 3 to the 33, and 2 to the 302. Combine those, we'll get 2 to the 310, 3 to the 33. So that's n. And it does have that nice little prime factorization. Fantastic. So then what did we need to do? It was squaring something, right? Square the exponents and the bases, add them up, and we want the last 3 digits. So 2 squared plus 3 squared plus 310 squared plus 33 squared. So we have 4 plus 9. 33 squared is 1089. And then 310 squared is 96100. And if I add those up, we get 97202, and we want the last 3 digits. So it should be 202, and that's going to be A. So there we go. So we can bubble in A, and we're done. However, I think this is an interesting question, and I think you could sort of really generalize it a bit. And so my challenge to you would be to do that. You know, talk about a set A that goes from 1 up to K, and talk about sort of an M-tuple free set. If S is in capital S, then MS is not in S. And then count the number of maximal subsets that are M-tuple free. The largest possible M-tuple free subsets. Count them up. You're going to use almost the exact same work that we've done here. Okay? There's nothing special about 3 that told us that, sequences of length 6 give us 4 choices. And so you could do something very interesting, probably come up with sort of a generalized result based just on what K is and some logarithms of K. And I think that'd be kind of nifty. So that's my challenge to you guys. And if you are up to it and you have a way to do it, or sort of an answer, if you want to do something specific, like tell me, oh, by the way, if K is equal to 1 million and we're talking about 7, septuple free sets, then there are this many maximal septuple free sets. That would be a wonderful thing. A little exercise for you guys to do to take what you may have learned in this test, this video, at the end of this contest, and just put it into practice. I always like it when a question can be generalized beyond just, hey, here's a math question. And I think this is a cool one. Anyway, that's going to be it for our 2016 Fermat paper. So I believe next I'll be uploading the 2016 Hypatia. Same level, but it's more of a written contest rather than a multiple choice contest. And if that interests you, I will see you there.